One of the limitations of PUMA compared to all metal scopes is its susceptibility to vibrations. This video gives tips on how to minimize this issue and introduces a new Exoskeleton Stabiliser module designed to reduce vibrations even further. In the first PUMA video, I gave a list of PUMA's limitations, one of which is the susceptibility to vibrations if the scope or desk is disturbed during observations. This is mostly a problem for the highest magnifications, where the effects of even tiny vibrations become highly magnified. Most professional microscopes don't suffer this issue to the same extent because of their all-metal construction. However, although PUMA's plastic frame makes it more susceptible, there are things you can do to minimize the problem, which I'll describe in this video. Also, after investigating the main sources of vibration, I designed an exoskeletal stabilizer system that clamps the optical tube to the focus plate and so reduces vibrations to a bare minimum, as well as reducing focus drift. This can be used in addition to the general measures, and I'll describe this clamp in the latter part of this video. The general things you can do to minimize vibrations involve tightening up the nuts, bolts, belts and springs, because these can become looser over time. However, you must be careful with this because over-tightening can damage or break the plastic structures. Specifically, 1. Ensure the timing belt is not loose, using the adjustable belt tensioners as described in the Z-stage video. There is an optimal level of tightening here, so it is not a case of the tighter the better. See the Z-stage video for details. 2. One of the reasons for vibrations is the fact that the Z-stage focus platform is suspended on springs. This source of vibrations cannot be totally eliminated without radically redesigning the focus mechanism, but you can reduce vibrations by increasing the spring compression. You can do this by rotating the top lock nuts down by about 1 full turn each over and above the default position that was described in the Z-stage video. Making these springs too tight can cause slippage and excessive wear on the focus gears, so again, it is a balancing act. 3. Ensure the focus post bolts are well tightened. Too tight, however, and you will crack the stage plate, so again, proceed with caution. 4. Ensure that the leg nuts and bolts are well tightened, again with the caveat that too tight can damage the stage plate. 5. Use the Z-motor mechanism for focusing. Details of this are given in the Z-motor video, so I won't repeat them here. 6. Ensure the articulation of the monocular tube with the filter block is not loose. Notice I say here not loose as opposed to tight, because there is a particular danger here that if you tighten this too much, you will break the small thread off the ocular tube, so not loose is as far as I'll go here. If you're using one of the mirror or splitter block ocular attachments, these will be fixed with a screw in this hole, so the issue of loosening will not arise with these. 7. Don't use the long legs system unless you really need it. Obviously, a scope on stilts will be more prone to vibration effects than a scope that is not on stilts. 8. If you must use the long leg system, ensure all nuts and bolts are well tightened, but not so tight as to damage the plastic. In addition, I recommend using flexible plastic M6 washers like these under the M6 nuts that hold the long legs attachment in place. These washers will allow you to make these nuts quite tight without damaging the plastic, and the elasticity of the washers serves 2 more effects. 1. They will prevent these nuts from working loose with time, and 2. They will act as vibration dampeners. 9. Put anti-slip vibration dampeners under the feet. I recommend using blue tack or white tack. 10. Finally, all these measures are only as good as the sturdiness of the desk and floor used. So, use a well-constructed bench or desk and preferably sited on a non-vibrating surface, like concrete. You may not have all these things available to you, but if you do, use as many of these features as possible. Once you have done all the above, you should notice a distinct improvement in stability, and any vibrations that do get through should dampen down very quickly. You can, however, go even further with the aid of stabilizing brackets, discussed next. While looking into the causes of vibration susceptibility, I came to the conclusion that there were 2 main vibration susceptibility points in the construction of the scope itself. The first is the fact that the focus platform is suspended on springs, and taking the measures described in the previous section should help with that. The second was play at the quick release articulation joint, where the optical tube mounts to the focus platform. When newly printed, this fits nice and tightly. However, over time, this can wear and become a bit looser. This is a particular problem for two reasons. The first, as you can see here, is that it can wobble. The second is that it can very slightly unwind during use. Even though this unwinding is very slight, the fact that this has a coarse spiral articulation means that even this slight rotation will cause the optical tube, and therefore the objective attached to it, to rise up and move further away from the specimen on the stage. With low magnification objectives, you won't notice this, but with high power objectives, even this slight rise will manifest as a change in focus and can be annoying. Thus, to prevent this motion at the quick release articulation, you have two options. 1. If you're using the advanced filter block, ensure you use either the augmented reality projector or an epi-black body light sink in the front port of the filter block, and fix this to the front clip of the focus platform, as was discussed in detail in the video on the AR projector. This will ensure the quick release mechanism cannot rotate loose and will also reduce linear movement at that joint. 2. If you're using this simple filter block, then until now you had no options. However, I've now designed this new exoskeletal stabilizer module for use with the simple filter block that not only articulates to the front nut of the focus platform, but also has these two side struts that clamp the optical tube to the focus platform by the sides as well. In addition, these struts clamp onto the ocular tube on top of the filter block to reduce any play at the monocular tube filter block articulation as well. This system therefore reduces motion in 3 degrees of freedom: the XZ plane, the YZ plane, and axial rotation. This new stabilizer system is currently only usable with the simple filter block and simple monocular and C-mount monocular tubes. You can't use it with the advanced filter block or any of the angle adjustable ocular heads. In the following section, I'll describe this new module in detail. These are the parts and the tools you'll need to build this stabilizer module. As usual, the first step is to clean up all the 3D printed parts and remove any supports and adhesions. The 3D printed parts comprise an axial component, a threaded clip, an insert, and 2 side struts. Inside the axial component are hexagonal sockets to accept 4 M4 nuts, so insert those and ensure they are pulled all the way into their sockets as shown. On the front of the axial component is a 3D printed thread socket designed to accept this threaded clip, which goes all the way in as shown. These holes at the side are for optional M4 grub screws. Only one would be sufficient, which can be used to ensure the clip does not have any play in its fit, but these may not be required if the plastic thread fit is sufficiently tight. Take this small insert component and fit it in the recess for it, as shown. You can now proceed to secure the axial component to the simple filter block with the M3 screw, as shown. Once fitted to the scope, you won't be able to change or insert an objective, so select the objective you're going to use and insert it now. The front clip swings into the AR stay thumbwheel socket on the front of the focus platform and is secured there in a manner that is similar to the AR clip used with the AR projector or EPI black body light sync. See the video on the AR projector for details of how to do this and adjust and tighten it. In an early prototype of the axial component seen here, I made the front clip an integral part of it to be printed as one. However, this narrow waist area is a potential weak spot that could separate along the layer lines over time. So, because this axial component is large and takes a long time and a lot of plastic to print, I decided it would be better to make the clip a separate small component, so that if it does break, then you would only need to print this one small component again, instead of the whole large part. While I'm on the subject of vulnerable components, I found that this clip area on the AR stay thumbwheel did have a tendency over time to break in this way. And you can see here one that failed. This is because this part is only held on by a very narrow area composed of only a few print lines of plastic. So I took the opportunity to improve the design of this part by extending the adherent surface area with a curved buttress as shown here. So if you've already printed this for your AR projector or EPI black body, just bear in mind that an improved version is now available if you need to reprint it. So far, this axial component will secure the simple filter block, similar to how the AR clip will secure the advanced filter block. However, to improve stability even further, I made these two side struts. These are designed to be a force fit to the sides of the focus plate, and they slide on like this. These need to be a tight fit to work well, so if you find that the fit is loose, you can address that by simply adding some sticky tape either to the focus plate or to the slot in the strut. If you want to make an even more secure fit, I made these two holes at the bottom of each lateral strut, so you can insert M3 grub screws to clamp the struts to the focus plate, but these are not necessary for casual use. Once the struts are in place, you must line them up with the holes in the axial component on both sides and insert the M4 screws without washers to keep the holes aligned, but do not thread the screws through the internal M4 nuts just yet. You'll notice that there are two holes on each side. The lower hole is to hold the strut against the filter block, and the upper hole is to hold the strut against the ocular tube. In this way, the struts act as splints to stabilize the joint between the filter block and the ocular head. However, I do not use the metal screws to directly apply pressure to these components. Instead, I designed the sacrificial insert we cited earlier to act as an intermediary and prevent damage to the optical tube parts from the screws. Now screw in your preferred ocular head tube and make sure it is not loose, either the standard one that accepts an eyepiece or the shorter C-mount version. And now you can secure everything in place by tightening up the 4 screws. The 16mm length of these screws is important because they have a dual action. The tip of the screw applies pressure to the insert, which in turn applies pressure to the filter block and monocular tube. At the same time, the pan head of the screw applies pressure to the outer wall of the side strut, so clamping the side strut against the axial component. If the screws were shorter, or if you used a washer, they would not apply pressure to the internal structures, and if they were longer, they would not apply pressure to the outer wall of the struts, and so the struts would not be supporting the internal structures. If you do only have longer screws, however, you could still use them and overcome this particular issue by using washers, preferably plastic ones, to make up for the extra length. I made this small insert a separate component because over time the metal of the screws will dig into it, as you can see here. so you may need to reprint it from time to time, but being a small component, this should be quick and easy to do. Alternatively, you could just put a small amount of 3D printer filament in the hole before inserting the screws to act as a shim and make up for this wear. So, if you fitted everything as I've shown you, then you'll have stabilized and secured the optical tube to the focus platform, and this will reduce vibrations that would otherwise have been caused by the various articulations as described earlier. To illustrate the effect of these stabilizing measures, I've prepared some demonstrations with and without them. In all cases, both stabilized and non-stabilized, I'll be using the same specimen, which is an H&E stained histological section of a human skin biopsy, a ×40 dry optarch objective, and 2 camera methods, afocal eyepiece projection and direct-to-chip C-mount imaging. I'll also be using the full Curler illuminator, so the long legs stand will be used, and I use both stage clips and the mechanical slide manipulator simultaneously because the stage clips keep the slide pressed to the stage at all times when moving it around and so prevent focus drift. For the stabilized tests, in addition to the above, I use the Stabiliser bracket system and flexible washers on the long legs stand with anti-vibration tack under the feet. I also use tack to secure the eyepiece during afocal projection, and also to secure the camera USB cable, as you can see here on this pile of books, to prevent the cable moving or pulling on the camera. The stabilized tests are carried out in a downstairs room on a sturdy workbench. The non-stabilized tests have none of those extra features and are conducted in an upstairs room on an ordinary table. This first video shows the results with afocal eyepiece projection, and I start each test by deliberately tapping the stage so you can see how quickly the vibrations die down. I then manipulate the slide across the stage to various positions. The afocal projection method has the advantage of showing you the whole field of view, as if you were looking down the scope by eye. But the total magnification is not so great, so you can see that there is not much difference between the stabilized and non-stabilized setup with regards to noticeable vibrations at this level of magnification. This makes the point that you do not need all these stability enhancements for normal use of the microscope by eye. The real benefit of the stability enhancements comes into effect when you zoom right in to the highest magnifications, as you can see here with this direct-to-chip C-mount demo. First, the demo without the stability enhancements. Although the scope is usable with great care without the stability enhancements, it is only really free of vibrations when you don't touch any part of it. Also, vibrations take longer to die down, and the non-stabilized form will show image wobble with any nearby traffic or other distant source of vibrations. So, the stability enhancements described in this video are particularly important for imaging experiments at the highest magnifications of light microscopy. Now the same setup but with the extra stability enhancements. Although all vibrations are not totally eliminated, they are reduced, and those that get through die down a lot faster. This generally gives a smoother viewing experience when handling the microscope controls, good for demonstrations or chasing live specimens around the stage. This is also good for image capture, with multi-frame averaging, for example. Finally, compared to the wobbly footage of freshwater ciliates seen at the beginning of this video, I thought it would be good to show you how these stability enhancements can improve your ability to demonstrate live specimens at high magnifications, because these move around the stage and need to be followed and focused on. In this demo, any focusing is done by the focus motor. while there is still some disturbance caused by handling the controls. This is relatively slight compared to the case where no stability enhancements are used. These ciliates have been imaged using the same setup as for the skin biopsy specimen, but with the difference that I have a filter in the IID slot of the condenser to give Schleieren phase contrast, so you can see delicate features such as the flagellae and cilia. The use of this Schleieren method affects the colors more than usual here because I am not using a diffuser in the lamp holder. It also alters the point spread function of the microscope. These changes cause some artifacts, so I wouldn't pay too much attention to the color contrast in this footage. I'll need to do a dedicated tutorial to explain these phenomena in more detail. For now, just note that it is possible to do high-quality phase imaging of live specimens with PUMA using ordinary objectives and the stability enhancements described in this video. In summary, the PUMA wobble can be significantly reduced by 1. Tightening up components using a sturdy bench with blue-tack vibration absorbers on the microscope feet, a Z motor, and the short leg system if possible. And 2. Applying the new Stabiliser clamping system if using the standard or C-mount monocular tube with a simple filter block, or using the AR clip with an epi-black body or the AR projector if using the advanced filter block. These measures make it a lot easier to do high magnification imaging with PUMA. If you like this video, please hit the thumbs up like button and view some of the other videos on my channel. If you'd like to support the project, you can do that by subscribing to this channel and telling others about it. If you'd like to help me continue this work, take a look at my Patreon page, where you'll find additional content and early bird access to future videos. Thanks for watching.